Hi, I'm Adam Davis Kukolich, and today I'm exploring if a picture is worth 1,000 words. The research question I set out to answer is founded on the idea that multiple different forms of representation share a similar conceptual or meaning space. As shown in the diagram, we have two different forms of representation, both images and words, that share a similar semantic space. And if this proposition is true, we can ask questions like, do detailed captions of images partially or fully restore image classification accuracy when images are degraded? And similarly, can a clear image do the same when captions are sparse or vague? To answer this question, we use CLIP, an OpenAI model that allows us to turn both images and text into vectors in the same vector space. This work is important for a few reasons. One, there's real-world camera situations where signal input can be noisy or degraded, and if we could better integrate across multiple modalities, then we may be able to improve classification performance when one modality is impaired. Also, I think this empirical machine learning demonstration can shed light on cognitive science as it may illuminate some questions or experiments that can be done as it pertains to human concept fusion. There's also a few applications of this work: medicine, autonomous vehicles, and accessibility tools. And to give a spoiler, the answer is yes, provided there's a shared semantic space. Rich captions can indeed offset image degradation when optimally weighted. So the way that we set up this experiment is we started with 1,000 photos of cats and dogs, and for each we came up with 4 image degradation levels: 25, 50, 75, and 90%. We also came up with 2 captions per photo, a high information and a low information caption. High information being 45 words, the low information being 10 words. We then mixed these representations after we vectorized them by creating a composite or a blended vector using what we call alpha, where alpha is the weighting on images alone, and 1 minus alpha is how much we weight the text. So once we have these blended vectors, we were able to experiment across 3 different independent variables, one of them being image quality, another being caption detail, and another being how much we weight images versus text. We subjected the different vectors to classification using both logistic regression and support vector machines to make sure that the effects weren't biased toward a particular classification method. The results were interesting. We found that at high dropout levels, pixel dropout levels that is, the accuracy of classification actually drops by around 25%, which is expected. But somewhat unexpectedly, we found that even at high pixel dropout, the best accuracy for classification does indeed include at least a little visual signal, which points toward there being some information to be gleaned even from poor images. Lastly, we found that clean images stay strong across all levels of alpha. We also found that when you add text to degraded images, the quality or the level of detail of the text actually matters. So here we find that detailed text or high information text helps rescue classification more than low information text. And this difference actually becomes more pronounced as images become more degraded. This means that the quality of the language matters more than just the presence of language. We also found that as you sort of decrease the degradation, it's still important to include some of the degraded image. So here, even at 90% dropout, an alpha rating of 0.25 is the best classification. And as a rule of thumb, if there are thin captions, then you can cap the image weight below around 1/2 before the bad image starts to degrade the classification. Lastly, we found that the results do replicate across different types of classifiers. While logistic regression performs a little better than SVMs, we find the same similar shape across all of the experiments, which does point to the effects being classifier invariant or model agnostic. Here we learned that rich captions can rescue classification ability up to 25 percentage points when images are heavily degraded. We also learned that the weighting of images versus text is important, and if we could dynamically weight based on the quality of signals, that could even improve classification more. So I think that's an interesting area of research. Lastly, we clearly have evidence for a shared semantic space in machine learning contexts across 2 different classifiers, but there is an intellectual leap there to be made when you apply it to human cognition. And while we can't necessarily make that analogy one-to-one, I think this research does at least give insight into how one might go about an experiment on humans. For example, you could give humans degraded images and degraded text and see how well that they classify. Thank you for listening, and Long story short, yes, a picture is worth 1,000 words.